Well, folks, I'm going to talk about forces and Newton's laws here. Forces are described as what causes the motion. So if there's no force, an object stationary will keep staying stationary, an object moving will keep moving, which is why spacecrafts keep moving. We send Voyager 1 and Voyager 2 into the space and they keep going for years because there's no force applied on them anymore. The fact that when we push on a sled on the ice, it stops a bit later because there is a friction force applied to it. So there's no force, there's no change in motion. Force causes the motion or change in motion. Force is described as a push or a pull, and there's generally an agent applying the force, and force is a vector. As much as we define their strength, the strength of a force, we also have to define its direction. There are mainly two types of forces. Contact forces are that applies in contact, so two objects should be touching each other for the contact force to apply. And long-range forces does not need two objects to be in contact to apply. For example, gravity is a long-range force. No matter where we are on Earth, we don't have to be stepping on the Earth to be feeling the gravity. Here's examples showing how we will represent the force vectors. And a block is pulled by a string. String applies a force to the right here, and here's how we draw that force. And here we're pushing on a spring. The person pushes on a spring and spring pushes back. We all felt that at some point in our lives, and that's the spring force. And that's the gravitational force, what we call also weight. If we have more than one forces applied to an object will draw vectors of those forces. I'm going to draw the vectors here. This rope is pulling in this direction, so here we have a vector here. We can call this F1. We have another vector downward. We can call this F2. And then we can add these two forces as vectors to find the total vector. Here you see a method, what we call parallelogram method. We put the vectors beginning to same point, draw the vectors to direction and size, and then we complete a parallelogram. Diagonal will be the addition of two forces. This question tells we have these two forces and there's a third one added to them. When we add that third one, the total force is to the left. So let me draw the total force. And if the total force is to the left, which one of these could be the third force we should add? And the third force we should add should cancel this guy here and cancel that guy and give a bit of additional left strength. We look at these forces in these type of questions. Generally it's best to go with the components methods. Remember, we find x and y components of all the forces, add x's to get the total x and add y's to get the total y. So I'm looking for a force that will have component that is down to cancel F1 and left to cancel F2 and add a bit more force, so we'll have a total force to the left. What I'm gonna do is I'm gonna look at the components of these vectors. F3 would have an upward component and a left component, so that cannot cancel F1. It's upward. For F1 to be cancelled, we need a downward component, right? So it can't be F3. We cancel that. Not F3. F3 can't be this. Can't be A. Here this force can cancel F2 but cannot cancel F1, so it can't be that either. When I got to this force, I'm gonna look at its components. There's a down component can cancel F1, and there is a left component that can cancel F2. And I can see that the left component is a bit larger than F2, so it can cancel F2 and give us a little bit of left over to give the total force of the net force, or the net force to be to left. So this guy will work. D will not also work because it can only cancel F1 but not F2, so it's not D. So our answer is C. We'll be talking about various forces in this section, so it's a good idea to have a description of those initially and shortly. As we use them, we'll go back and remember them. One is the weight force. It's simply the gravitational pull of the earth on an object on or near the surface of the earth is called weight. And here's how we describe weight. Weight is equal to mass of the object times g, which is the gravitational acceleration, and the approximate value of g is 9.8 meters per second squared. We should keep in mind that mass and weight are not the same thing. Mass is the amount of matter a body holds, and it's the same everywhere. So we stay on Earth and or go to the moon, to the Mars, the mass will always be the same, but weight will change because weight is the gravitational force applied to us, and times our, it's mass times the acceleration due to gravity. And acceleration due to gravity changes from Earth to the moon or to the other planets. So our weight will change if we go from Earth to moon, but our mass will stay the same. Second force we'll be talking about is spring force. We all know that if we compress a spring, it will push back. If we stretch a spring, it will pull back. So it will always apply a force against what we're trying to do, and that's the spring force. Here I'm compressing. If I push this block to the left, I will be compressing the spring, and spring will be pushing back on me. And if I pull the block to the right, then spring will be stretched and will be pulling back on me, always against the force we try to apply to. Always find the direction of spring force using logic, and the value of it is k times x. Just look at the absolute value of this. Book describes this as minus kx, many books, but that's just showing that it always is against the force we apply to the spring. So once we find a direction with the logic using that idea, we can just go ahead and find the absolute value, which will be the magnitude of the force. Saves a lot of algebraic mistakes, so go ahead and use this version. And here k is the spring constant and x is the amount of stretch or compression. And third force is the tension force. If we pull on a string, pull an object with a string like the sled over here, the string will have a force which we will call tension force, and we'll show those forces as well as vectors. We can also draw it on the string. I like drawing them on the string. It just helps me to see that it's along the string. So that's the tension force. Fourth is the normal force. Whenever we put an object on a surface, the object will be pushing on the surface, and the surface will be pushing back. That will be the pushing back force. It will be the normal force. And keep in mind that the normal force is always perpendicular to the surface that applies it. That's why it is called normal. Normal is for perpendicular. We'll use small letter n for the normal force, and again it's always against the force that pushes on the surface. If we are on an inclined plane, the normal force again will be perpendicular to the surface. So here our skier has a weight down. Let me delete the weight out of. I have the alright, got stuck here. So our skier has a weight down, right? And that weight has a component along the surface. Let me pick another color here. Has a component along the surface. And a component perpendicular to the surface. We talked about this before, what happens if we have a vector in this fashion and how to find the components, but this component will be mg sine theta. This component will be mg cosine theta. Theta being the angle that the incline makes with the horizontal. This will always be the case, so keep that in mind. So the perpendicular force applied to the surface in this case will be mg cosine theta, and normal force will be opposing to it. Again, I like showing the forces on the object, so I'm going to show the normal force here in this fashion. So there will be a normal force because there is a push on the surface by the weight, and it's opposite to whatever that push is and equals to it. This is mg, by the way. So that's the normal force. In the atomic level, we actually compress springy-like behaving atoms, and they push back on us. Kind of a springy atom force is the force that is becoming normal force. Friction is like a normal force exerted by the surface, but it's always against the motion and along the surface. If a sled is going on the surface in this direction to the right, there will be a friction force to the left. If I'm trying to move an object to the left, there will be a friction force to the right. So friction always tries to stop the motion, always against the motion. And there are two types of friction forces. One is the kinetic friction and one is the static friction. Both are found using friction constant times the normal. So if we're finding a friction force, we are interested in what is the normal on the surface at the time when we are calculating that friction force. We'll find that normal force. There are ways to find it, we'll get there. And friction force will be friction coefficient times the normal force. And the same for static friction. The only difference is friction coefficient slightly changes if an object is moving or if an object is stationary. So if an object is moving, we will have what we call kinetic friction constant. And if we have an object stationary, we're trying to move it but it's not moving yet, then we'll be using static friction constant. Generally they will be given to us, or the force and normal we could know, and we might be asked to find a static friction constant. As we solve problems again, we'll go back and remember, and we'll see some problems in another video. Here is the normal again on the second picture. Alright. Additionally, there is a drag force. Mainly will be drag due to fluid. It could be water, it could be air. Mostly we'll be dealing with air. And in most cases in this course, we will be ignoring the air friction or air drag. So keep that in mind, unless you're asked explicitly to include air drag. We will be excluding it, ignoring it, because in most of the cases it's not big enough to include. Sometimes it is important if we have a very large surface area and small mass, like in a guy flying with parachute. Thrust force is mainly applied by engines. There's thrust force in the airplanes, thrust force for the rockets. That will be included, and mainly will be calculated using some given values. Electric and magnetic forces are due to charges, either stationary or moving charges, and it's not going to be covered in this course, but just know it's due to charges. Alright, these are forces. Again, they are vectors, and we have these type of forces. One thing we're going to do is identifying all the forces applied to an object that is stationary or moving. Here's a question practicing that. A bobsledder pushes her sled across horizontal snow to get it going, then jumps in. After she jumps in, the sled gradually slows to a halt. What forces act on the sled just after she's jumped in? We'll be making what we will call free body diagrams, where we will be drawing all the vectors that applies to the object of interest. So we're going to make an ugly picture as always. So I'm going to make a sled. So she pushed the sled and then she jumped in. Initially when she pushed the sled, she gave it a velocity, so it's going as an initial velocity. It slows down and stops because there is a force, what we call friction. So there will be a friction force, always against the motion. So if I want to draw it, if I assume the motion is to the right, friction force will be to the left. So that's the friction. There will also be, as always, if we are on Earth, there will be the gravitational force, which is the weight. It should be a straight line here. Let me undo that. So downward gravitational force, another force that applies to the object, and there will also be a normal force upward. It is suggested to take the object as a dot, take it aside, and apply all these forces, but I actually like applying them on the object. We can just put a dot on the object and apply them all there, just like this. So we have mg here, which is the weight. You can also call it weight. Downward we have kinetic friction in this case, because the object, the system is moving, and we have normal force. The surface will apply a normal force, and the answer is gravity, weight, and normal force, and kinetic friction. That's it for the forces. We'll talk about Newton's laws in the next video.